Hello, happy Friday, and thank you for joining me today as we take a look at section 4.6. Maybe you picked up on this from our last section, or maybe you glanced ahead a little bit, but in terms of eigenvalues, we can have real eigenvalues like we looked at 4.4 and 4.5. Or we can have complex eigenvalues. And if you're keeping tabs on some of the patterns that we see here, our last section in chapter 4, 4.7, will be about repeated eigenvalues, which we looked at a little bit with the real eigenvalues, but we will kind of dive into a little bit more in 4.7 next week. So complex eigenvalues always occur in conjugate pairs, just like our normal complex roots. They will always come in conjugate pairs. So we will take a look at that. And basically, if you have an eigenpair, the conjugate is also an eigenpair. This actually, with complex, makes our job a little bit easier because typically we only have to solve for one of the one of the complex eigenvalues, and then we use its conjugate to kind of form the other one instead of having to solve. So let's go ahead and do an example here of when this occurs. Here's our differential equation, and this is what we're using as our matrix for A. So let's go ahead and find the determinant of A minus the lambda identity matrix. Should look like this. And we get 1 minus lambda squared, and then plus 1 equals 0 is what we're setting it equal to here. So we get lambda squared minus 2 lambda. We will get a positive 1 from squaring this binomial, and then adding the other one here will give us this as our quadratic. So doing our quadratic formula to solve here, this is not factorable. So quadratic formula is going to look like 2 plus or minus the square root of 4 minus 8 is what we're going to get as our discriminant there, all over 2 times a, which would be this. So we are going to get the square root of negative 4 under here, which would obviously be plus or minus 2i. So this reduces to 1 plus or minus 2i over 2, which would be I. Okay, so what we're going to do, and this was where I was saying this is going to make our job a little bit easier, is that we are going to use 1 plus I to find an eigenvector. Okay, where our job gets a little easier is that the conjugate of 1 minus I will give us a conjugate. So let's say we'll yield a conjugate eigenvector. Okay. All right. So that is good news for us. We're only doing half the work that we would have had to do before. So the process is going to be the same as we're used to. We're going to go ahead and say our lambda sub 1 is equal to 1 plus I. Now, where some of this work is the same is nice, where we go to plug this in, find our general solution will obviously look a little different because we have these complex pairs, but we will talk about that, cross that bridge in a minute here. So if we do 1 minus our lambda, which is 1 plus I, we get a negative I left over. These will remain the same. Okay, again, 1 minus the quantity 1 plus I will give us negative I here. So there's my matrix. We are solving here for x sub 1, x sub 2 to find our first eigenvector. Okay, now this is kind of tricky to solve here because obviously we are looking at getting solutions that will have imaginary numbers in them. So what I'm going to do is I'm going to go ahead without doing any row operations here. I'm just going to use R1. And I'm going to write out the equation that I get here with R1. So it looks like negative I x1 plus x2 equals 0. All right. So that is my my equation that I'm trying to solve here and figure out what's going to work for x sub 1, x sub 2. And kind of like similar to the past, we're going to make some educated guesses here. So what I'm going to do is I'm going to go ahead. I just want some positive values here. So x2 is equal to I x1. And if that's the case, then it looks like I could probably just call x1 something imaginary here. So that way, or I guess I could just call this 1. If I just call x sub 1, 1, then x sub 2 just has to be I. And I guess that's pretty easy right there. Okay, so we're going to go ahead and call our eigenvector x1, 1, and I. All right, so there's our first eigenvector. And going back to this fact that I pointed out up here, we used our first complex pair to find an eigenvector. Our conjugate will yield a conjugate eigenvector. So what that means is that if we use lambda sub 2 of 1 minus I, we don't have to plug in, work anything out. X sub 2, that vector, will be the conjugate of this. So I'm going to get 1 and I'm going to get negative I right there. Okay. And so this is where I say that kind of makes our work a little bit easier. So we found our eigenpairs. That's the good news. The tough part of this is going to be to get this into our general solution here. So I'm going to go ahead and rewrite. We had lambda sub 1 is equal to 1 plus I, and we got our x sub 1 and lambda sub 2 and x sub 2. Okay, so remember that no matter what, when we do our general solution, that it does take on this form. Oh God, I did not lock these into place. Okay, this is what our general solution is going to look like. So that part is no different here. So my y of t will be c sub 1 e to the lambda sub 1. So we're going to have 1 plus I times t, and then multiply that by our eigenvector. And same with our second solution. All right, so my general solution looks like this. However, we cannot leave it like this. So one thing to remember is that we don't want, for whatever reason, we're okay with having some imaginary in our solution. We're just not okay with having it up here in the exponent. So if you remember what Euler's formula says, it's that if I have e to the a plus bi times t, that we basically separate that out as e to the at, the real part, and e to the b times I t, so the imaginary part. And it's that imaginary part that we went through and we derived, but we basically found that this will give us e to the at times, and then this turns into cosine of bt plus I sine of bt. And hopefully you remember this from our previous units where we solved and we had complex roots. So let's go ahead and apply that here now to what we did with each of these. So we should have c sub 1 e to the at. So it looks like I'm going to have just e to the t. And then we are going to have cosine of bt. Well, b is also 1. So cosine of t plus I sine of t. Okay, times our eigenvector. So we would have that times 1 and I right there. Okay, now if you just bear with me just a second, I'm not going to do the second one this way just yet, okay? Because what we're going to do is we're going to investigate what this looks like when we actually simplify here and distribute this through. So basically, I'm going to do my multiplication that I'm being asked to do right now. And not only am I going to multiply this e to the t through here, so actually I'm going to just do that right below. I'm going to combine two steps. So I should have e to the t cosine t plus, I guess we put I out in front. I times e to the t sine t. Okay. Now, the reason why I wanted to do that is we're going to multiply it here and put this all into matrix form. So if I multiply it by 1, e to the t cosine t plus I e to the t sine t. If I go to multiply it here by I, I'm going to have a little switching between my imaginary and my real. So I'm going to have I e to the t cosine t. But here where I multiply it by this term that already has the I, I'm going to get a negative 1. So it looks like I'll have negative e to the t sine t. Okay, so we are going to separate our real and our imaginary terms at this step. And I want to point out the reason why I'm not doing this with our C sub 2 right now is because you can see that because this just included the conjugate pair, we're going to get something very, very similar to this. So essentially what's going to happen up here, if you went through and did this, is you're just going to have some positives and negatives that change. If all you're doing is changing by a scalar multiple of -1, that gets wrapped up into this C sub 2 value right here. Okay, so essentially what we're doing is we're kind of just wrapping this all together. And I'll bring it back here in just a second. But yeah, we're going to get something that's very similar. So when I go to separate out my real and my imaginary, I'm going to go ahead and take C sub 1 times the real portion of this, which from this first element would be e to the t cosine t. From the second element here would be the negative e to the t sine t. And, because we don't want to reuse C sub 2, I'm going to say I have I times C sub 3, and I'm going to pull out the imaginary parts of these elements. Okay, so I pulled out the I, so it looks like for the first element, e to the t sine t. And for the second element here, I pulled out that I, so I'm going to have e to the t cosine t. Now, I know I'm kind of going through this, and this is a very confusing topic, so you just let me know if you have questions, or you can obviously go back and kind of replay this, but this is tricky for sure. Okay, so what we're going to do here, because like I pointed out, if we were to do this with our second eigenpair up here and do all this multiplication, this will only differ by a scalar multiple of -1. We're going to go ahead, instead of calling this C3, we're going to call everything we did here I times C3. We're going to just call this C sub 2. So when we go to actually separate out the real from the imaginary, all of the imaginary components of this are going to get put into this, rolled in, and just called C sub 2. Okay,